Welcome back to Chapter 11. In this chapter, we're going to get a hint, a little taste of what calculus is. In this section, we're going to be looking at limits in motion and the tangent problem. We'll be looking at limits again more in depth in Section 3. This just kind of touches on it so that we can get that issue with the tangent problem. Specifically, we're going to be looking at the slope of a tangent line. Shouldn't be a problem because in order to find the equation of a line, we just need the slope of a line, we just need 2 points. However, a tangent line only hits a graph in 1 point. So how can we find a slope if we only have 1 point to work with? That's the tangent problem. That's what we're going to see today, and that's actually one of the huge topics behind calculus. Our learning targets for today, we're going to calculate the average velocity of an object during a time interval, which is remarkably easy. It's just total distance divided by total time. We'll see that in a second. We're going to find the instantaneous velocity of an object at a given time. Instantaneous velocity would be the distance gone in 0 seconds divided by 0 seconds. That's the same issue that we're going to have with the tangent line. So we're going to see how we can deal with that. We're going to find the slope or equation of a tangent line to a graph at a point. We've been talking about that. We're going to find the derivative of a function at a given point. Spoiler alert, that's actually going to be the exact same thing as the instantaneous velocity and the slope of a tangent line. And we're going to find the derivative of a function, which honestly, when I find the derivative of a function at a given point, I find the derivative of the function and then plug in the point. And that's what I'm going to show you how to do as well.
So average and instantaneous velocities. We saw this a bit in that chapter P activity. An average velocity is just the distance that has been traveled divided by the time that has been elapsed. So we have just the final distance minus the starting distance divided by the change in time, or change in distance divided by change in time. Another way that this could be written, as opposed to delta t, a lot of times we write it as an h instead. It just helps to keep the equations just a little bit less daunting. Like one Greek letter out of it helps a bit. And so, if we wanted to find an average velocity, we'd want something to find it of. So let's say a rock falls from a height. Its distance can be measured by y equals 16t squared. It's projectile motion just dropping down, where y is the distance traveled and t is the time in seconds since it started to fall. So if we wanted to find the average velocity for the first, say, 2 seconds, what we would do is we have the final distance, that would be f of 2 minus f of 0, because that's where we'd start at 0, go to 2, over change in time was 2. So we'd plug in 2, we'd have 16 times 2 squared, minus plug in 0, 16 times 0 squared, divided by 2. 16 times 2 squared is 4, times 16 is 64, minus 0 over 2. And then 64 divided by 2 is 32 feet per second is the average velocity as the rock is falling for the first 2 seconds. Now the rock starts out not moving at all, and then it speeds up. So it's going to start out slower and end up faster, but the average velocity is 32 feet per second. Same thing as I'm driving into work every day. I don't always go the same speed, but the my average velocity is going to be the total distance divided by the total time. It's 11 miles divided by half an hour makes me go 22 miles per hour on average. Yes, sometimes I'm going faster, sometimes I'm stopped, but that's what the average velocity is. Now, an instantaneous velocity, that's going to be the velocity that it's going at a specific time. Now, the problem with that, as we saw in chapter P, is that at a specific time, there is no change in distance and there is no change in time. So we end up with 0 divided by 0. So we can't find an instantaneous velocity as itself. However, we can find upper and lower bounds for it. We can find what the fastest and the slowest it could be is. And so to do that, we would find we're using the same thing, and we're just looking at 2 seconds. So this would be from 2 seconds to just over 2 seconds. So sometime over 2 seconds could be at 3 seconds, could be at 2.1 seconds. We don't know. We can change what that h is. And this one's from just under 2 seconds to 2 seconds. So we can look at an average velocity right above and an average velocity right below the time in question. And that should give us bounds for the instantaneous velocity. Like, what would it be at that point? Now, we can't just plug 0 in for h here, because if we do, we get 0 over 0 still. So that's problematic. We can simplify, however. If we simplify these, I'm going to take this one over here. We have delta y over delta t is going to equal 16 times, we can distribute that, 4 plus 4h plus h squared minus 16 times 4 over h, delta y over delta t equals, we can distribute to get 64 plus 64h plus 64h squared. Nope, 16h squared. How could you guys let me do that? That's 16h squared, because there's not a 4 in front of that one, minus 64 over h. And then what happens here is we have a 64 minus 64. Those guys disappear. Now everything has an h in it. We can factor an h out. 64 plus 16h over h. The h's cancel, so our delta y over delta t for the time interval just over 2 seconds is going to be 64 plus 16h. Now, if we do the exact same thing with the other one, we can follow along with the same steps, and we're going to get delta y over delta t equals 64 minus 16h. It's going to switch places there. So what we have is we're going to have one that's just a little bit bigger and one that's just a little bit smaller. Now, if we take values of h and we plug them into a table, we're going to get a table, but we're going to get a table that's going to go right down here in this left-hand corner. So I'm going to erase just a little bit of this, because it's definitely going to cover up what we're going to look at. If you didn't get it, it's gone. You'll never see it again. There's no possible way you could rewind this until before I started erasing and see what I had just erased. So that's a pity. All right, so now we have our table here. And so if we're plugging in 1, it's from 48 to 80. It's a pretty big gap. But as we're plugging in smaller and smaller numbers, we get numbers that are really close to 64. And so we'd imagine that that's going to be 64 because, and that should make sense, as h is getting smaller and smaller, this 16h is getting smaller and smaller, and so it's just getting closer and closer to 64. So if h is 0, we'd think, hey, that's going to be 64, but h can't be 0 because it's still undefined in that original equation. So, but we can get really, really, really close to 0, and the upper and lower bounds are getting it closer and closer and closer to 0. And what that is, so what is a derivative? Derivatives have some meaning. Derivatives can be the slope of a tangent line to a curve at a given point, instantaneous rate of change, velocity or acceleration, depending on what we're talking about. But the biggest thing that derivatives are, what is a derivative? A derivative is a slope. That is huge. The derivative is a slope. We were so close to finding derivatives at the very end of chapter 1. It's ridiculous how close we were. And we're just going to pick up right from where we left off and take that one last step to take it from just the difference quotient to a derivative. And so these are definitions, it's more meanings of derivative, but that doesn't help us figure out how to find a derivative. To find a derivative, we're going to look at what's called the limit definition of derivative. The limit definition is the derivative of function f of x is the limit as h approaches 0 of f of x plus h minus f of x over h. This was the difference quotient we were looking at the end of last chapter, except we weren't taking the limit as h went to 0. We made h, which at the time we called delta x, we made it just something really small. We used 0.01. But now we're going to make it smaller and smaller and smaller. So really, we're finding the slope as these 2 points become 1 point. And that is the derivative. It's as those 2 points get closer and closer together, that line that they're making, if you connect the dots, gets closer and closer to being an actual tangent line instead of a secant line. So that's the limit definition. We're going to use this a lot, at least today. There is another slight variation to this equation. It could also be the limit as a goes to b is f of b minus f of a over b minus a. Same idea. It's taking the slope between 2 points as those points get closer and closer and closer to each other. This one uses 2 distinct points, whereas the first one uses 1 point plus a slight difference to that point. Honestly, I use the top one almost always. The bottom one is easier if you are finding the derivative at a certain point, but even for that, I use the top one, and we'll see why later on when we do an example. So, before we get to an example though, let's look at some notation. Calculus was developed by a couple different people simultaneously in different places of the world. Well, kind of different places in the world. I mean, it was still Europe. It may have been developed elsewhere. We just don't know about it because we don't. But even in Europe, it was developed by a few people at the same time, and they used different notation. Of the people that have notation, we'll see Leibniz's notation, Lagrange's notation, Newton, because Isaac Newton developed it, and Leonard Euler also developed it. Interesting side fact, my cat's name is Leonard, after Leonard Euler. So um, anyway, but of those 4 types of notations, we really only use 2 of them. The other 2 have their uses in, I want to say, fairly obscure topics, but it's not necessarily obscure topics, but topics that we're just really not going to get to this year. So looking at the types that we'll use, Leibniz's notation, so we have a little bit of history. So the derivative is slope. It's change in y over change in x, or delta y over delta x. But since the change was so small, use a lowercase delta. The lowercase delta looks like that, which for convenience, maybe sloppiness, it just became d's. So for Leibniz's notation, the derivative is dy over dx, which we could also use if we have a function. We can go d over dx of the function. For example, if we wanted to have the derivative of the inverse sine, we could write d over dx of inverse sine of x. So it doesn't have to be just dy over dx. It could be this. This type of notation is very useful when we are dealing with partial fractions, implicit differentiation, a few more things that we will get to later on this year. It's also nice when we are like listing rules, because I could just have d over dx of sine inverse of x equals whatever it equals for its rule. We don't have to define the function first, like we will for our next type of notation. And this type of notation is Lagrange's notation. Now, funny enough, this is not even the funniest name we're going to see in the next couple weeks. But this one's also known as prime notation. I'd say, at least in the beginning, this type of notation generally tends to be more common. It's what I'll use more often, and it's easier when we're working with functions. But prime notation, if we have the derivative of function f of x, that's f prime of x. The derivative of y is y prime. And so you just pronounce the apostrophe as prime. And so this one, if we were doing the limit notation, for function f of x, f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. If we wanted to define a function like the inverse sine function, we'd have to say f of x equals inverse sine x, then f prime of x equals whatever that's going to equal. And we will get to that, but not in this chapter. And so those are the types of notations we're going to use. I wanted to get that done before we do an example, because it's hard to talk about a derivative, especially as an equation, without having the notation to use with it. So let's look at how we find the derivatives using the definition. And this is what you're going to be doing in this section, by the way. So if we have a question, find the derivative of f of x equals x cubed. So to do this, we're going to use the limit definition. F prime of x will equal the limit as h goes to 0 of f of x plus h minus f of x over h.
That's just the definition. Like, we haven't inserted any content there. Now we'll insert some content. F prime of x equals the limit as h goes to 0. F of x plus h is going to be x plus h cubed. X plus h cubed minus f of x is x cubed over h. So if we just plug in 0, we're going to get x cubed minus x cubed over 0. It's 0 over 0. That doesn't do us any good. We need to distribute this x plus h cubed. So luckily, for the past couple years, you've been learning about binomial distribution, which makes that so much easier. And I know for a fact that your teachers would have told you that this is important because you're going to use it in the future and it's going to make your life so much easier, and you listened and so you understand it. And so that's going to be wonderful. I'm so happy for that. But when we expand this x plus h cubed, we're going to get x cubed plus 3x squared h plus 3xh squared plus h cubed. And then we have this minus x cubed at the end, right? That's not the binomial expansion, that's just this minus x cubed all over h. So now we can start simplifying. Looking at the top, we have some like terms. We have x cubed minus x cubed. Those will end up canceling each other out. And then what else? Like, what does all the top now have in common? They all have an h in them. So let's factor out an h. F prime of x equals the limit as h goes to 0 of h. What we have left will be 3x squared plus 3xh plus h squared all over h. The h's will now cancel, leaving us with no fraction. So now if we plug something in, we're not going to get 0 over 0. So let's plug in 0 for h. F prime of x equals the limit. No, we don't need the limit anymore. We're plugging it in. So f prime of x equals 3x squared plus 3x times 0 plus 0 squared. Well, 3x times 0 is 0. 0 squared is 0. Those go away. So we're left with f prime of x equals 3x squared. That is the derivative for x cubed. This is the process you're going to be using quite a bit. And there's really two ways. There's finding the derivative, which we just did. We end up with an equation. And there's finding the derivative at a point. And so a lot of times you actually start out with that. Use the other formula, the f of b minus f of a over b minus a, and you find that limit. And that's great. I don't start out with that. I actually start out with this because now if we wanted to find it at, say, x equals -1, we would just plug -1 in for x. -1 squared is 1 times 3 is 3. If we wanted to then find it at x equals 2, plug in 2. 2 squared is 4 times 3 is 12. We wouldn't have to go through the steps all over again. We have a function. We can plug in whatever numbers we want into that function to get the derivative at that point. And so finding the derivative at a point all on its own, yeah, it's nice, but it's not as useful. That's why we started with this. We can find the equation, and then we can plug in whatever point we want. So let's see one of those. Find the derivative of f of x equals x squared plus 2x minus 7 at x equals 2. So the same steps. f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. And yes, I tend to write down the equation every single time because now I can plug stuff into it. F prime of x equals the limit as h goes to 0. F of x plus h means we're going to plug x plus h into both the x's. So we'll have x plus h squared plus 2 times x plus h minus 7, and then minus the function, x squared plus 2x minus 7. X squared plus 2x minus 7. So if you look on the side of your phone, you can see the rest of that equation. The parentheses are there. If not, let me know. I'll bring my Sharpie over and I'll put the parenthesis right where it goes. So we have that, and that's all over h. We need to multiply some stuff out. F prime of x equals the limit as h goes to 0. X squared minus 8, or x squared plus h, remember, is not x squared plus h squared. Don't be that guy. It is, however, x squared plus 2xh plus h squared. We can distribute the 2 here, plus 2x plus 2h minus 7. And now distribute this negative. That's key. Minus x squared minus 2x plus 7 all over h. We can cancel what we have in common because we will be able to cancel stuff we have in common. We have an x squared minus x squared. We've got a plus 2x minus 2x. And we have a minus 7 plus 7. Those can all cancel. Everything from the f of x will always be able to cancel, leaving everything that's left has an h in it, always. With polynomials, when you get to like trig, it's a little bit funnier, but with polynomials, that is always the case. So we can factor the h out of those remaining terms. F prime of x equals the limit as h goes to 0 of h times, we still have a 2x plus h, and then plus 2 all over h. Cancel the h's. And now we can plug in 0. F prime of x equals 2x. The h will become 0 plus 2. Now we wanted to find it at x equals 2. So we just plug in f prime of 2 equals 2 times 2 plus 2. 2 times 2 is 4 plus 2 is 6. So f prime of 2 equals 6. And again, this is nice because if we have part 2 of the problem saying, all right, now find what it is at x equals 10, we just need to plug in 10. 2 times 10 is 20 plus 2 is 22. And we can get it from anywhere. So these are the two basic types of questions that you'll be doing. Yes, you'll be doing a bit of expansion. You'll be doing a bit of multiplication. That comes with the territory. But this is using the limit definition on only polynomials. I'm only throwing polynomials at you. You don't have to worry about exponential functions today, or logarithms, or trig, or anything like that. We'll get to those later. But keep working problems, keep asking questions, and until next time, happy mathing.